as I wrote to my email of last week, we've come to an end of our passive understanding of relativity. I should rephrase that. Our understanding of passive relativity, that's how I should put it, in the sense that everything that we've done up till now is looking at nature doing its stuff and wondering what it looks like from one inertial frame to the next. That's all we've done so far. As promised in my overview of the first lecture, today we're going to start with doing some active relativity, in the sense that we're going to not just look at what nature does and how it looks from one frame to the next, but also how the rules of interacting change from one frame to the next. So just to give you a small little bit of overview, you know how this works in, say, Newtonian physics, right? If you're looking at mechanical things, and let's not worry about quantum mechanics at the moment, just classical Newtonian stuff, masses moving and you pushing and pulling on the thing, then everybody knows that the rule that you have to do to solve that is something like this, right? Newton's second law. And if it so happens that the mass of the object happens to be a constant, which is not trivial, right? I mean, if you have a rocket boosting to the moon and it's losing fuel because it burns it away while it's going up, then this is certainly not a constant. But most exercises that you typically do and encounter, you can assume m to be a constant. Then you know that Newton's second law typically is given like this: F equals m times a. Now, we need a rule like this in special relativity. You cannot use this rule as is. Any idea why? We already, tangentially spoke about it every now and then, but maybe you can recall why this rule will probably not hold in special relativity. There's a couple of reasons, but maybe you can come up with some.
I guess acceleration is not the same for every observer.
That is absolutely correct, of course. Acceleration, well, is that true actually? Acceleration not the same?
Yeah, I think so, because the amount of time is different.
That is correct. So one of the reasons that this rule will not hold in special relativity is because A is defined like this. Well, one thing you know is that the dv's themselves, or excuse me, the dt's themselves are different for one inertial frame to the next. So obviously the amount of acceleration might change from one inertial frame to the other. So that means all of a sudden this rule will give you different outcomes in different inertial frames, right? So that is one reason. Another reason maybe why this might not hold in other inertial, in special relativity. We came to talk about this about 2 lectures ago. If you don't recall, that's fine, but I'm just curious.
Was it Felix's comment that then some force would go infinite or something like that?
The force will become infinite. Now the force is something external, yes? So you put this in from the outside. So there's no a priori reason to say relativity gives you infinite forces, but I don't think that this is what you mean.
Yeah, it was like that if you let the time run for a very long time.
Yeah, but here, as long as you put the gamma in front of t, you should be fine, because the faster you go, so the higher dv is, the bigger the gamma would be. So the bigger, the smaller the gamma becomes. So then gamma dt goes towards.
V becomes bigger, yes? At bigger v.
Yeah, right. So the bigger the gamma becomes, so the bigger the dt, because you multiply it with the gamma.
Depends on whose delta t that is. If you're going to use time dilation, right, and you squeeze a gamma in there, depending on whose time this was to begin with, you could either have a dt or a d tau, right? I mean, the rule that we derived was this. Or more general, the Lorentz transforms. And what I hear you do is that you say, well, you can replace this dt by maybe this thing, you get an extra gamma, and maybe the extra gamma will do something.
Yeah, because the extra gamma is going to stretch the amount of time.
That's correct.
So then the acceleration goes towards 0.
That is correct. That is correct. In fact, that's an argument that we did, I think, last week or 2 weeks ago, that I actually showed that there is a version of Newton's second law that actually already has built in that you cannot go faster than the speed of light. But it's not built in here, is it? I mean, there's absolutely nothing here in this rule of physics that says that you cannot go faster, or that you cannot go faster than light. Now, it might still be true that you cannot go faster than light, right? We have proven all kinds of properties about light. We have proven, for instance, that if somebody sees something move with the speed of light, then any other person will as well. That's what we proved. In one of the tutorial exercises, we also proved that if somebody in some inertial frame sees something move with the speed of light, then any other person, if somebody will see something move with less than the speed of light, any other person will also see the thing move with less than the speed of light. Do you recall that exercise? It's very important that you do. So we proved at some point, a couple of weeks ago, that if something comes flying past here, yes? I think we took a vacuum cleaner back in the day. Guys, you are really on the microphone right now. So if a vacuum cleaner flies by, and I watch it move, and it goes slower than the speed of light in my frame, then in any other inertial frame, so any person who has a velocity with respect to me will also see that vacuum cleaner fly slower than the speed of light. It's a different velocity, right? That's the velocity, Einstein velocity addition rule, so the velocities are different. But it is true, if any observer sees something move slower than the speed of light, any other observer will as well, even though their speeds might be different, they're all both smaller than the speed of light. So what that shows you is that apparently the speed of light is some kind of barrier. Not only does everybody see something move at the speed of light, then everybody will. No. If only one person in the entire universe sees a vacuum cleaner go with less than the speed of light, any other observer will as well. So that's what I mean by barrier. There's no way that you can go to any other inertial frame and all of a sudden the vacuum cleaner will move faster than the speed of light. So there's something about the speed of light. So that strongly suggests that speed of light cannot be, you cannot go faster. Now this does not have that built in at this point. There's nothing stopping you from saying, you know what, I'm going to apply a constant force, right? Just take your particle in an electric field, for instance. Stretch out the electric field until infinity if you want, so that the charged particle will accelerate more, and at some point will go faster than the speed of light. In fact, a couple of weeks ago we did this exercise where we actually solved how that would look, right? We did the Jacob particle accelerator, we calculated what that would look like. Now, all of these are just different ways of saying that there's something not completely right about this rule if you want to apply it in special relativity. So we need some version to update it. That's what we're going to do today. I have two learning goals for this lecture. One of them is I'm going to show you the rules of energy and momentum in special relativity and how they are connected to each other. And that's one. Secondly, I'm going to do this by what we call Lagrangian mechanics, or Lagrangian formalism. Now I remember in our introductory lecture when we started that I gave you an overview what we're going to do each week, and when I said Lagrangian mechanics or formalism, I heard this groan go through the audience. People are not fans of Lagrangian mechanics apparently, or some people are not. Now let me make that my personal third learning goal for today, that hopefully by the end of the day you will see that Lagrangian mechanics is actually well, maybe the best thing you can. I was about to say tight, but then I realized I might not have the right age to say those words anymore. Okay? But Lagrangian mechanics really is the way to go if you want to do theoretical physics. This rule, if you want to apply physics with this particular rule, comes with all kinds of drawbacks. And the only reason that you might be more familiar with this one or might be more relaxed with this one is simply because you're used to this rule more. It's the way that you were taught when you were studying physics. And secondly, it very much agrees with everyday intuition. Yes? I mean, what the rule really says, if you push against something, it will start to move. That's what the rule says. It also says if you push a little harder, it will accelerate a little bit faster. Now, my cat knows this rule. Okay, my cat is one of those animals that just knocks cups off my table and everything. So my cat has some sensation of Newtonian mechanics in her mind. She might not be able to do the calculation, and she might not really be able to calculate if I tap it with this velocity, then that cup will end up exactly over there and hit the mouse or something like that. But she does know tapping things means accelerate. So this rule is very much in line with your intuition. So here's the bad news. The Lagrangian physics part is going to be not so much in line with intuition. That is the bad part. The good part is, well, there's a whole slew of things why Lagrangian mechanics is good. And we're going to hit each of these marks as we go along. And again, hopefully by the end of today you will say, you know what, Lagrangian mechanics is really one thing that we do. Now, theoretical physicists almost exclusively use Lagrangian physics. There's hardly any Newtonian physics done. If you ask Jacco, hey Jacco, give me the Newtonian version of the strong nuclear force, he will laugh at you. Okay? What he will do instead is give you a Lagrangian. And Lagrangian is, well, this thing that sort of replaces what we call a force. So, because of all these advantages of Lagrangian physics that we're going to hit today, you will understand by the end of today why people like Jacco use Lagrangian physics and why we in theoretical physics never use Newton's law anymore. So, again, 2 learning goals. One of them, show you the rules of energy and momentum in special relativity. Secondly, show you how Lagrangian mechanics works. And my third personal learning goal is make you feel that it is tight. Okay. All right, now, just out of general interest, is there anyone who happens to know a rule for energies and maybe even momenta in special relativity? Don't tell me where it comes from. Do you know maybe a formula that tells you what the energy is?
E equals mc squared.
E equals mc squared.
Is it plus pH? No, it's not plus pH. It's plus p something.
Plus p something?
PCs.
Is it PC?
Yeah, but you have to put squares, extra squares.
Well, the units
and
have to be okay,
everything.
yes? And the units are not fully correct right now.
E square is m square c to the power of 4 plus p square c square.
That's the rule. If you want an equivalent way of stating this, is gamma mc squared. It's a different mathematical formulation, but it has the same physical content. Remind me, I'm going to make a comment on that later when we've actually derived this. What you typically hear in the books and everything is that they leave out the gamma. They say E is mc squared. Please, if you have that in your mind somewhere written, throw that in the recycle bin of your mind and press delete, okay? E does not equal mc squared. E equals gamma mc squared. Okay. Now, where does this rule come from? Any ideas? I mean, I'm sure people know the rule, yes? You feel like you came up with the rule, the above one. Where did you get it from? Do you know it by heart?
Yeah, pretty much.
Anyone else? An idea?
I mean,
You could say Einstein. Einstein already came up with this version of the rule in a follow-up paper to his 1905 paper where he introduced the Lorentz transforms of special relativity. He based on his Lorentz transforms, he came up with a new idea for energy, and he wrote an article on that in the same year that he published special relativity. So he already came up with that formula. It's a nice little paper, by the way. The English translation is something like, does the energy content, or does the inertia of a body depend on its energy content, question mark. The answer is yes, via that rule. So you could say, well, Einstein came up with it. Maybe you could say, well, measurement tells you where that's true. Sure. Yes.
He came up with it without the gamma?
No, the whole formula.
Ah, the whole thing. Okay.
Yes.
Hit.
I mean, really, we should. I mean, I might, if I have time, I will post it on a lane to that paper. It's really neat. He does it again using a thought experiment, the Gedanken experiment, and he comes up with this rule. It's really beautiful the way that he does it. But as you know, we're going to do it in different ways today. Okay, but people do know the formula, yes? E is mc squared, even if you never realized that there should be a gamma there. All right, we're going to derive it. And before even starting with the Lagrangian mechanics, I'm going to do it in a quick and dirty way. And when I say quick and dirty, it's still correct. But it's the way that I think is easiest. So, let's get started. In the previous weeks, we have built up all of special relativity from this statement. Yes? In the first week we started by saying, well, the speed of light is invariant because electrodynamics tells you and you can measure that that is the case. Then in the second week I said, no, but then later people realized the special relativity is not a consequence of the speed of light itself, it's a consequence of space and time. And then we replaced the statement, the speed of light should be invariant, by the statement, this should be invariant. And everything that we did from week 2 onward, we derived from this. Yes, we got Lorentz transforms from this. We got time dilation from this, we got Lorentz contraction from this, we got the Minkowski space-time frames from this. Everything that we've done all came from this and only this starting point. The quick and dirty way of deriving rules for energy and momentum is going to use the exact same rule. We're going to use that as a starting point and just do some algebra on it, and then we get this rule that you see there above. Yeah? So let's do it. So we're going to take this as fact. I'm going to do a couple of algebra steps. Now, if at any point you think, wait a minute, you're doing something algebraically that is mathematically not correct, please interrupt me. If not, I just keep on writing, okay?
Squared is not d squared anymore on the left side.
That is correct.
Step 1.
Is it better?
Yeah, no, yeah.
Okay. And you know what? Let's write it like this. I put a little arrow on top of the x, which is just another way of saying x, y, and z direction. Right? I made it a vector. Now, this is where we are right now. The only thing I did was a little bit of algebra. Now I'm going to make an observation. This guy looks a little bit like a velocity, doesn't it? I mean, it's the amount of distance traveled in a certain amount of time. There's a square, so it's a velocity squared maybe. It certainly has the units of a velocity, right? This is proper time. This is the amount of distance, so it is a velocity squared. And that sort of makes it look like a momentum. Because what is a momentum? A momentum, classically speaking, is mass times velocity. Right? I already raised it, but in Newton's second law, P equals m times v. Well, there's sort of like a v here going on. So let's try if we can sort of massage it algebraically into a momentum. No, don't laugh. I mean, as long as I do mathematically allowed steps on both sides of the equation, I'm still correct. I'm still just manipulating my Minkowski line element. Yes, I'm manipulating it in a particular way, but I'm still mathematically and physically correct. So that's what I'm going to do. What I want to do is make sure that there's an m in here. Now, if I want to really get this into momentum, what I'm going to need now is not an m, but an m squared on both sides. So, I'm going to multiply both sides by m squared. But you're just working your way towards the answer. Fine. That's the quick and dirty part, yes? But please note.
But then you're assuming that energy is invariant, right?
Yes, and I'm going to make a comment on that, but thank you, because there's a nice little bridge there.
I think you might have missed the square on the left side. Or it's MC, I don't know.
Yes. There we go. It's another way of saying I need another sip of coffee, okay? So I made this statement now. Again, the quick and dirty part is that I'm, of course, obviously working my way towards the expression. In that sense, it's quick and dirty because I know what should come out. But please note that the steps that I'm taking are mathematically and physically completely allowed. So, in that sense, I'm not smuggling or something. I'm not putting any stuff in that wasn't in there already. Now I'm where I wanted to be because this is now sort of like a velocity times a mass. So you might think, you know what? It's like a momentum now. Yes.
You can't really say that it's a velocity because dx is for one observer and
yes,
tau is
thank you. I'm so happy with that comment. Because look, a momentum classic in Newtonian physics is m times v, right? So let's call it classical. Is by definition m times v, right? Let's make it a vector. And that means that it should be this. That's classically what we define as a momentum. Now, this point, I mean, you're completely right. This number, dx over dt, is not the same as this number, because this is dx over d tau, and a dt is not a d tau. There's a time dilation in between. A velocity, if I want to see how fast my vacuum cleaner is flying, what I do is I define my coordinate system. I see how many meters it flies, that's my dx. Divide by how many seconds it takes on my watch for the thing to fly that many meters. That's my dt. I divide these two numbers. Then I get multiplied by m. I get my p, my momentum. But now we have a different situation. We now have a flying vacuum cleaner. I measure how many meters it flies. Yes. Then I don't look on my watch how many seconds that took. I'm asking the vacuum cleaner how many seconds that took. Right? The vacuum cleaner doesn't measure my dt, it measures d tau, the proper time. So what I have here, this velocity is sort of, well, for lack of a better word, like a bastard object. You take the amount of meters in one frame, and you take the amount of seconds in another frame. Correct? So it's not really a momentum. Now,
can't we just contract everything with gamma and then we get dt over dt, which is 1, which is kind of nice. Then we get the actual momentum.
Let's do that.
Gamma m squared.
I'm going to follow your advice. I'm going to take this guy, this thing that we now sort of constructed in. Yes. And because I want this thing to be really expressed in a momentum, as in my amount of time and my amount of meters, I have to make this d tau turn into a dt, right? Now, fortunately, we know how to do that because we know that there's a formula for time dilation that tells you how to turn any d tau in any dt. You just squeeze a gamma in between. You have to place the gamma at the right place, okay? Because if you recall, dt is gamma d tau. The gamma is correctly placed because d tau is defined as the amount of time as seen by the vacuum cleaner in this case, because the two positions for him were at the same place. So using this rule, I can replace this d tau by a dt. I get this. And what I now see is that this m and this really is now the velocity as seen by me when I see the vacuum cleaner fly by. So this m and this dx dt really is the classical momentum. So apparently what we see here is that this guy is not the classical momentum, it's gamma times the classical momentum. Yeah? Okay, that's easy enough. Now we're going to make a definition now. We're going to call gamma times classical momentum, we're going to call it the relativistic momentum. It's just another way of saying I don't want to constantly keep writing gamma times original p, I'm just going to define a new p for brevity's sake. And this guy, this needs definition, I call the relativistic momentum vector. From now on I'm going to drop the rel part, yes? Whenever in the next 2 weeks I write p, I mean relativistic momentum exclusively. And if I do mean classical, I will write classical, but I'm going to drop the rels. You'll see this in all the books. Every time that you read any text on relativity or theory of relativity is applied, whenever you see p, it's the relativistic momentum. So there's that guy. Now, having done all that, this, now p squared, this part. So we now have this. Now we have this thing to worry about. Okay, this is for now a solved issue. We have this other guy, dt d tau, and an m squared c squared in front. So yeah, what to do with that? Yes, Emma. Sorry, where?
M.
On the left.
M.
That's the second time I made. I cannot. Usually I just sort of wheeze my way out and say, well, the c's are 1 anyway. Not with m's in this case. Yes.
It's a gamma.
This, yes, correct. Yes, thank you. So this is now solved matter for now. We're going to worry about this thing, what this thing means physically. Yeah. This d tau, correct. Well, that is a gamma, isn't it? The relationship between d tau, dt, and d tau is time dilation. That's gamma. So really, what this guy says. In fact, let's make another side note here. So we have m squared c squared dt d tau squared really is m squared c squared gamma squared. Okay. Again, this is all just algebra. I haven't really done any physics. The only thing that I did was something looked like something that I know from physics, namely momentum, and I sort of made it look like that a little bit more. I'm going to make a claim. This guy is energy. There might be a c missing somewhere, but aside from a c or a c squared, that thing has a physical interpretation of an energy. That it might not be obvious at this point. Because look, it's a mass squared maybe. In fact, let's remove the squares for now. You can put them back in later if you want, but it's just an m and a c and then a gamma, a Lorentz factor, and I say, well, that's an energy. And it might not be obvious at this point why that is. So I'm going to show you, first of all, that it is an energy, but most importantly, why it is an energy. Okay? I might need a little bit more space. Just put in the definition of gamma. We derived it in lecture 1.
It's c squared if you want to.
Not yet. Here it is, right? No, this is c squared.
There.
Not
The
yet.
energy is not energy.
No, I just took all of this without the square and I put it here. So we will see that it is an energy aside from maybe a c or so.
Yeah.
So we might be a c off, but it will be an energy aside from that missing factor of c. It will present itself as we go along. Now, still algebra. Now let's see if you remember this particular step that I'm making now from the tutorials.
Oh, is that if it's smaller than
Binomial
x?
approximation.
Binomial approximation, you could also call it Taylor series.
Yes.
You might recall that at some point during tutorials when we're doing an exercise where things were going so fast with the speed of light that we replace things by epsilons, right? The deviation from the speed of light. And then I said if you have to do calculations where numbers are very close to other numbers, then you can use the following approximation that this is true. That's a mathematical fact. It's called the first order Taylor approximation. And I'm just applying it here. You see that? Maybe for people who need an intermediate step, what I have here, 1 over the square root is the same as this guy to the power of -1/2. And if you assume that the vacuum cleaner or whatever you're looking at isn't going too fast with respect to the speed of light, then this is a small number, especially when you square it.
Shouldn't that be then 1 plus 1/2 v over c squared?
I agree, thank you. Good. Correct. I mean, there's a minus here, and there's a -1/2, right? That's this end there. Should give you another, etc. Gives you a plus. Correct. Thank you. It means I need another sip of coffee. One of those things. Side note, I'm very close to in my research getting to a particular result. So I spent literally until 2 o'clock every morning just making that outcome come out. It's not there yet, unfortunately. But I noticed it with these little thingies that I miss, squares and minuses and everything. So this is not a didactical trick, as in see if you are all paying attention. You really have to keep me straight here, okay? We're still okay. Now look at this. So we have now looked at what this object is at the moment that the vacuum cleaner, whatever is flying, is not going too fast with respect to the speed of light. Then this approximation holds, and this expression becomes this. I get mc plus 1/2 m v squared 1 over c, yeah? Again, algebra. Look familiar? Classical mechanics?
Kinetic energy.
It's the kinetic energy. So, you know what? I already said, well, there's probably some superfluous c somewhere. So, but what I see here then is multiplied with, I see this. Agreed? Now, you know from Newtonian mechanics that this part must be an energy. It's in 1/2 mv squared. It's the energy of the thing flying by. Now, relativity then tells you, well, there's this extra part that comes with that energy. That has nothing to do with how fast it is flying. It comes with the mass itself. Yes? This is why people say E is mc squared, because they only talk about this part. The real energy is this part as well, and actually it's all of this, because I cut off the expansion, yes? This approximation, if you want to make it more accurate, you have to add more and more terms. But just as to show you that this must be an energy, it looks like this. So, I get the strong suspicion that all of this, based on what we see here, is, well, it's like an energy, sure, divided by c. It literally gives you back the classical energy, what you would expect in classical physics. Right? If I ask you, there's a mass flying here, and you just leave it alone, so you're not touching it, you're not pushing or pulling, you just leave it closed on its own beam. And I would ask you classically, what is the energy? You would say, well, there's no potential energy. So the only energy that it does have is 1/2 mv squared. Well, apparently this is what this flying mass, the flying vacuum cleaner, has. So that gives a very strong suspicion, going back here, that all of this mc squared, mc gamma squared, that this mc gamma, as you see here, is an energy over c. Yes?
You have a 1/c, but you also have an mc squared. Doesn't that mc squared take out the 1/c?
No, what I did here is I had this mc here without the square, and I took an extra c outside of the brackets. Okay, this is why it becomes mc squared. This is algebra again. So if you work out the brackets back, you get exactly this point here. So, now at this point you might think, yeah, but wait a minute. You identify this as the energy, sure, over c, but only under the approximation that the thing is not flying too fast, right? That's the way that I concluded it. Maybe this expression is not the energy at the moment that things are not going too slow and I'm not allowed to make this approximation. My claim is it's still an energy. Can somebody give me an argument for this? You see the question, yes? I made an approximation so I could identify it as an energy, because then it looks like classical energy. Then I make the statement, no, it's actually still the energy if you had not made the approximation. Yes?
Well, I mean, what you're having on the left is before the approximation. Then you make an approximation to show that in cases where it's going slowly, it is definitely the energy, but then your conclusion is about the original thing before you make the approximation, so you should be fine.
So you're saying something like this. This is all of it?
Yeah.
Yes? So there's some physical interpretation of this thing. We looked at a small piece of it. We concluded this must be an energy. I mean, I'm paraphrasing what you're saying, but this must be an energy. Well, you know, if this is an energy, but it's part of the bigger thing, then all of this must have been an energy. That I think is your argument.
Yeah, well.
That's correct. It's a good argument.
Sounds like a generalization, but
Sorry?
sounds like a generalization.
Okay.
Yeah.
But
Can't you just continue the
Series?
series until you get bigger and bigger by adding more terms? Shouldn't you reach the higher speeds then?
Yeah, I mean, the number will change, definitely. The expression will change. You get more terms, yes?
But does that mean that it will not be energy anymore?
Well, that is my question, really. At the moment you have extra terms. Does it prevent this thing from still being called an energy? I mean, sure, it's not going to be 1/2 mv squared anymore. The number will change, but we'll still have the physical interpretation of an energy. My claim is yes, but I need you to understand why the answer is yes.
Well, I mean, if you expand the Taylor series your factors that you get at 1 over n factorial, so it's going to get smaller and smaller, right?
Agreed.
So can you say that all the concurrent terms that are going to follow are going to approach 0 and therefore it still holds?
So your claim now is that the series will actually converge, the finite number will come out,
Yeah.
which is mathematically an interesting question, but it's not physically the question that we're looking for. Yes.
What if this is classical energy, and we are here all the time assuming that V is much smaller than C? Maybe if we did not assume that, we would get some kind of relativistic version of kinetic energy.
I agree with that, but that again is rephrasing the statement. So you're saying, well, if you had not done the approximation, you get some other thing, and we call it the relativistic energy. That's correct. But why it's still an energy? The answer is yes. So don't worry about the conclusion. The conclusion is that it's an energy, but I need the argument. Yes.
Isn't the dimensional analysis will be always the same? No?
That's correct. Thank you. That is what I was looking for. In physics, are you allowed to add things together that are not the same object? Can you add an amount of decibels to an amount of liters, for instance? Does it have any meaning? Yes. At the moment that you have any physical quantity, the only thing that you're allowed to add to it and still have the same physical quantity is if it is the same stuff. Yes. Now, nature, or mathematics, actually, I should say, gives us it's a sum of stuff. Now, that means if you can only identify one of them as being an energy, then the rest necessarily has to be energies as well. That's enough, the dimensional analysis. So yes, all of this, well, aside from the 1 over c, is really an energy. And the only reason that I did the Newtonian approximation, that I say V is small, is to be able to identify at least one term as an energy. And then we use Jonas' argument, and then the rest must be energy as well. Yes.
But just that you're adding, well, so the question, do we know that K is also energy? For sure.
1/2 mv squared.
Oh yeah, right.
When literally it is, we were well, at the moment.
Yeah, no, okay.
Yeah.
But
We're looking at a mass flying with a velocity v. Yes.
the question, or what I'm wondering is, because what you're saying is as long as you add stuff, it has to be the same stuff, because if you once you add different things together, it has no physical interpretation anymore.
Yes.
But since we're only doing this, like the entire derivation is only based on math, not on physical
That's wrong.
concept.
No, that's wrong. I understand where you're going, but everything we got from here, that is a physical statement.
And the Taylor series is gonna always, like, you add.
Yeah, no,
it's
that's true.
like
Yes. No, I do
series,
understand.
It's always the same.
If you would have just a mathematical exercise and you would add stuff to it, you have no business identifying the extra stuff as energies or what have you. But remember, we started from physics.
Yeah, no, okay.
Now, to make a long, so again, the only reason I went to the Newtonian approximation is to show you that at least one term in this whole expression is an energy, because I can identify it with kinetic energy, classical physics, and therefore from the dimensional analysis, the rest must be an energy as well. Now, obviously, this expression, all of this here is an energy. We're going to drop the Newtonian approximation at this point. Yes. Again, it was only to show you that the thing comes out as an energy. So all of this, that's my conclusion now. All of this is energy over C. That's what we found. Now, having gotten to that conclusion, we go back to this statement, right? We're identifying this thing, and we're identifying that thing. And now we have this beautiful equation. Continue here for a moment. M squared C squared equals E squared C squared minus P squared. That's what we found now. It's a direct consequence of our invariant Minkowski line element. Now you have this. That's it. That's the quick and dirty way. We now have the expression. I have a couple of comments to make, but maybe you can. There are subtleties here, but I'm sure you That is a good
There
starting point.
You said mc squared plus k equals energy, and you say that mc squared is then kind of potential energy.
That's
No.
not what I said.
No?
No,
But-
I said there is a certain amount of energy that comes with the mass.
Okay.
Yes.
But you already, like, isn't it kind of what we were trying to go for, and then you're using it to get there?
No, not really, because the mc squared that you're referring to is in here. There is also an mc squared, ultimately somewhere here-ish, but that came from here. So what I sort of, if I'm paraphrasing now, so you have to correct me if I'm wrong, but what I sort of hear you say is, well, this guy already has an mc squared in it, so why is there another here? Something like that.
Not really, because
Okay.
like you said, so we had this expression mc squared plus kinetic energy, and you said that
In
is
the low
total-
velocity approximation, sure.
that is the total energy, but for that
Yes.
you already have to have some knowledge.
No, that's a classical total energy. Then I went back before I made the approximation and I said I'm just going to call this the full energy.
Okay.
Yes. Again, the approximation only made to show you that it is an energy to begin with. Then I dropped the approximation, now we're here. So we have this expression now, yes? Good. That's the quick and dirty way. In the tutorial I'm going to ask you to show that this is mathematically equivalent to this with the gamma. It's a mathematical exercise. It's not too hard, just requires a couple of steps of algebra, but I do want to focus on it a little bit.
I'm sorry, a question.
Yes, no please.
When you say you dropped the approximation, didn't you get E over C due to the approximation?
No, I only got the interpretation of an energy due to the approximation.
Okay.
So I made the approximation just to show that the expression that we have,
Mm-hmm.
mc dt d tau,
Mm-hmm.
is an energy aside from the c.
Oh, okay.
So I only use the approximation to show you that it is an energy.
Okay.
I am not using the approximation to actually give the expression for the energy. It's just the interpretation that I did there. Now, we're here now. Again, tutorial, I'm going to ask you to show that this is true. Before we continue with the real derivation, this is the quick and dirty way, let me show you a couple of things that you should immediately keep in mind when you start working with these formulas, yes? First of all, this expression is mc squared 1 minus v over c squared. That's apparently the energy of a flying vacuum cleaner in relativity. Yes. Is it invariant? So will the number come out the same for observers in different inertial systems?
No, it will change.
How? Why?
Because if I fly, the vacuum cleaner flies past me, or
Yes.
if I'm flying with the vacuum cleaner, my gamma will be different.
Correct, or you can say the v will be different.
Yeah.
Yes.
Yeah.
The vacuum cleaner flies by and I measure it will go this and this fast. Remember, our v now really is the v as measured by me as the thing flies by, yes? So I can measure what its velocity is. Now, so if I then use this formula, I will get some expression for how much energy the vacuum cleaner has due to its flying with respect to me. But if I start chasing the vacuum cleaner, then in the new coordinate system, the thing will have a lower velocity. Using the Einstein addition rule, you can even calculate how much lower it will be, but it will be a different number, and that means the energy will be a different number. So it's not invariant. Different observers will measure different numbers. Okay? So that's one statement. Another statement, is it constant? So so forget about going to another different inertial frames. It's just me in my inertial frame seeing the vacuum cleaner measure now its energy and measuring 2 seconds later. Will the number come out the same?
Yeah.
So long as it's not accelerating.
Correct. You can see there's no time dependence here. Well, there might be a v because somebody's pulling on the accelerator, or Jacob put the accelerator, charged it and put it into his particle accelerator or something like that. Then it will have some acceleration. Then energy will not be conserved. Okay, fine. So we know it's an invariant. It's non-invariant. It is also not a constant. So next time I ask you on an exam, give me an example of something that's not an invariant and not a constant. Here's one example.
Wait,
Is it not constant?
Not
For
an
constant
invariant.
V, it is
Under the right
constant.
conditions.
Yeah, well, yes.
Yes.
So
So
the
when
difference,
I phrased the exercise on the exam, I said, if your answer depends on the context, please state the context. So yes, a non-charged vacuum cleaner flying through space, left alone, will have a constant energy. Okay, but it will not be. But it will not have an invariant energy. Now, suppose that I fly along with the vacuum cleaner. What will its energy be in that particular frame? So if vacuum cleaner flies, I choose an inertial system where the thing is constantly next to me, so at rest.
MC squared.
Then it will be mc squared, because then the v will be 0 in my new frame. So,
But
this expression reduces to mc squared, the famous one, E is mc squared, but only under the condition that the thing is not moving with respect to you. Yes?
does that mean that the conservation of conservation of energy
Yes.
only holds as long as you stay within the same inertial frame? So once you switch inertial frames, that would work anymore, right?
But
Yeah,
I
but-
mean,
yeah, but
that's the same for.
I'm going to let him.
Newtonian.
I'm sure he's going to give
I
an
mean,
answer.
with Newtonian physics, you have the same thing, no? If I'm in the plane, I see a bird flying by, it has a different kinetic energy than from somebody being on the ground,
Yeah.
right?
No, of course I do get that. I'm just wondering how that works out in the end.
Let me give you a short answer.
Yeah.
So let's take sitting on a plane and you see a bird. You say, oh, well, compared to the plane, the bird has this and this velocity and therefore this and this kinetic energy. Then you say, well, let's go to a different inertial frame. I'm going to change this guy's energy. Okay? Not because I'm pushing or pulling on the bird, but because I just switched to a different inertial frame.
Mhm.
You're sort of cheating at this point, right? Because you're not really proving the conservation of energy. You're just going to another inertial frame. But suppose that you do that. In order to go to a different inertial frame, that means either you have to have slowed down or you have to have sped up. That itself costs energy. So switching inertial frame itself costs energy, and that missing energy, that energy that you need, might be the exact energy that you see the thing at a different value.
Quite sure it isn't.
I see a nice tutorial coming up. Anyway, the point here is, as long as V is, as long as the bird or the vacuum cleaner is accelerating, or it's being sped up in a particle accelerator or something like that, you cannot assume this energy, this new expression, to be a constant. It is never an invariant. Now, going back to my question, what happens if you go to an inertial system where the thing is at rest, the vacuum cleaner, the bird, what have you? Then this number is going to be mc squared, yes? So that means that there is a particular amount of energy that has to do with the mass of the object, right? You cannot get away from that. You cannot make the mc squared go away in this expression. You can make the additional parts due to the 1 over gamma, that you can switch up. If you go to a different inertial frame, then the 1 over gamma is going to be a different number. So there's not 1 over gamma, 1 over the square root, so gamma here, this gamma here. Question, what is the lowest gamma can get?
1,
That's 1. And the biggest?
infinity.
No, not 0.
Yeah, 0 is.
No, also not ish. It's not asymptotically 0 is what you mean.
Infinity.
Yeah.
This is V, C, gamma. Yeah.
Did you ask the lowest?
No, I asked you the highest.
The lowest is
Okay,
1.
lowest would be 1 anyways. Yeah.
And the biggest is infinity. So that means the amount of energy, the lowest it can get is when gamma is the lowest, in which case gamma is 1 and you get mc squared. The biggest it can get by going to a different inertial system is infinity. But that means there's no inertial system where you can get lower than mc squared. That's what you find here. There's exactly one inertial system where the energy is exactly mc squared, and that's the lowest energy you can make the thing have. That has a very deep physical interpretation, because that means that mc squared really is a thing. It really has a physical interpretation. It's apparently it's stuck to the object. No matter in what frame you go, you will always have that amount of energy. Yes? That's very important that you conclude from this.
So no, it's like the rest energy.
We call this the rest energy indeed, mc squared, because it's the energy the thing would have at the moment that it's at rest with respect to you when v is 0. Another important interpretation of what we see here is sip of coffee. No, it's not the physics that I want to. My memory is lapsing. Let's see if it comes back. Oh yeah.
It helped.
It really helped. It did. I'll do some push-ups in the break so we get the blood flowing or something like that. Now, this other thing that I want to say was, we saw in the Newtonian approximation just now that this E, if the vacuum cleaner or the bird or whatever is flying not too fast with respect to you, then this was the expression, yeah? Okay. You get back into classical Newtonian physics. But when you did your course in classical Newtonian physics, either at high school or here, your teacher probably never told you about the mc squared. You never had to take it into your calculations, did you?
No.
I mean, if your teacher taught you about, there's some object flying or falling or whatever, you would probably say, well, the energy of that thing is kinetic energy plus big V potential energy. Yes? And then he probably also told you, well, this number has to be constant. We have not proven it yet. We will at the end of this lecture today. But if you know that this is constant, then you know that if this guy changes, the potential energy, because your flying pen gets higher or lower or something like that, right? They change the potential energy, then this one has to compensate. And in this way, you could do the exercise where, a flying pen at the moment that it flies up, its potential energy goes up, this number goes up, then this number must compensate, so the velocity goes down, which is true because the pen will slow down as it goes up. Some point will drop down again, and you could do all these exercises with flying pens and these sorts of things, right? You remember this from your high school. Yet you never had to take this into account. Well, we now see that in relativity, every mass comes with this additional piece, even when you make the approximation that you are in classical Newtonian physics. So, my question to you guys is, why did your high school teacher or whoever taught you classical physics never had you calculate this stuff when you did your flying pen exercises? Yes?
Is it like external forces, like energies that are inside? Because when you use just the kinetic and potential energies, just look at how the object does outside, but you never look at inside. So
I think I know what you mean. I mean, you never.
It doesn't change, and it doesn't change our results. And also when you
why not? Well, why could you not have a flying pen, and not only does it gain kinetic energy because its potential energy is right. If you have a drop of pen, its potential energy will become less and less and less. Then this guy must compensate, become bigger and bigger and bigger. Why can't you have the situation that, you know what? This guy can get bigger because the mass of the pen increases downward. You say, well, but masses of pens do not increase. Why not?
You need some
Mathematically, apparently, it's perfectly allowed.
I mean, that's exactly what happens when you have nuclear decay or fusion, fission, any of that.
So there are examples where that does happen, is what you're saying.
Yes, but if we're looking at Newtonian physics, usually your pen doesn't spontaneously decide to nuclear fuse
that's a good point.
and get some extra energy to
that's a good
lift
point.
itself up a bit.
That's a good point. So, so suppose you have this mass, yes? I'm just doing classical physics now. And here's the height, and here's just the amount of space in x direction or something like that, and the pen is flying. Just very basic high school classical physics. As the pen is flying, its height will go down. Because of the height going down, the potential energy, I removed it, but let me put it back. Potential energy in classical physics for height is this number here, mgh, where h is the height. If this number goes down, because the height goes down, this must go up, so the pen goes faster and faster on its way down. Yes? That's how you do your high school physics. But I'm really asking again the question, I'll get back to your comment in a second, but I'm going back to the question, if you now know from special relativity that this part should also be there, why does the decrease in mgh, all of it go into the kinetic energy and not in this part? And you might say, well, it's because the mass. There's nothing here that's time dependent, so how can this guy increase? Why not? Just make it a time-dependent mass. Maybe nature chose to make masses bigger as they went down. And this is your comment. I'll get to this in a second. Yes. Felix's comment was, but there are situations where that does happen. Nuclear events, yes? In nuclear events, you do, well, formula is going to be a little bit more complicated, but you have some part here. You have some part here. When it loses energy, it will actually gain in mass and the other way around. Right? This is where nuclear explosions and decays in particle physics get their energies from. So my question, why isn't this part gaining or giving energy, isn't really not that strange, because in nuclear physics that does happen. Yet in classical physics, we completely ignore that part. So I'm back to my original question. If you now know that physically this can happen, why didn't your teacher tell you that? Why did he always leave out this part? Sorry, Jonas, you were dying to say something, I think.
I don't have an answer anymore.
Because it's not intuitive.
Sorry?
It's because it's not intuitive, and you want to teach kids in high school.
Oh, yeah, no, that would be actually a very good thing. Yeah, you're right. So, well, the effect does happen, but we don't want to bother the kids with it. No, sure. I mean, it wouldn't be the first time that you have sometimes have to simplify things to make things didactically feasible. Yes.
But because what we did, like, there was exercises with the rocket going away and like losing mass, but they didn't put.
Well, that is actually
MC squared.
That's actually a good point as well.
But the sum of the mass stays constant still.
Well, let's take this. Let's take, again, still classical physics. Let's take a rocket that goes up, and it goes up by spitting out mass in the form of some fire, right? I mean, you make use of Newton's third law, that you push back against something, and Newton's third law tells you that something has to push back up. That's the gas that you're spilling out, and therefore the thing accelerates upward. This is how we make rockets go out. But that means certainly that this mass is not a constant. So again, my question really is not that strange. You can certainly have situations where the mass should have been time dependent. And again, we never take it into account in classical physics. Whereas relativity tells you maybe you should have.
Also, plugging it into your calculator when doing some little exercise in high school will just, because MC squared is just so much bigger, so it just gives you numbers that are unhelpful.
Okay. What if we are like only dealing in inertial frames, so in one inertial frame, so you are not moving with some velocity with respect to each other, and then the energy would then be MC squared, but if nothing is moving, I mean then you only have like potential energy.
Yes.
And could we then say that, I mean, it should be constant now?
Why?
Can mass like change without motion?
I mean, at the end of your exercise, you're still going to have that energy, right? Once the pen returns to ground, it's still going to contain that rest energy, right? So that's a thing that.
Well, that's my question. What does it?
Well, if all of the energy would be gone, if all of the mass would be turned into energy, would you still have a pen?
Yeah, but you still have MC squared, just with a different m. The answer is actually quite simple.
So your question is, why don't you lose mass why isn't mass time dependent?
My question is really why didn't you ever have to bother about the MC squared part when you did your very classical Newtonian
That's
exercise?
because Newtonian exercises don't deal with that part of physics. It's just like, if you, as we established, mass is time dependent if you look at nuclear physics, but Newtonian physics just deals with potential energy, and like it's just a part of physics that doesn't deal with the problem.
I understand. So it's just that the exercises that you used to do with these things were by choice blocked off from the situation where mass could have changed.
Because if you look at a spaceship that has a nuclear reactor inside of it, where mass gets converted to energy and shoots out, then you'd have to look at it.
I'm happy with that answer. I'm going to add a little bit to it.
Yeah, I was just going to say, isn't it for the same reason that you said that the E is considered constant if there's no change in acceleration? So.
Yes, but only under that condition. But in my case of my flying pen or my accelerating rocket, you certainly can have acceleration. No, guys, the answer is actually quite simple. Let's see let me just say it first and see if it connects with what you heard about this before. No, you know what? Let me do it by example. I'm literally going to take a pen. Now I'm holding the so let's say that the pen, I have a very extremely heavy pen for calculation's sake. It's exactly 1 kilogram. Okay, it's 1 kilogram pen that I'm holding now. I hold it about 2 meters above the ground. What is its potential energy at this point? You know the formula: N times G times H.
18.
Yeah, 19 point something.
Yeah, 90 something like that. Let's make it 20. Let's just say the G is about 10. Okay, just for the sake of my argument. So you would say 20 for this energy, yes?
20, yeah,
Okay.
joules.
Which 0 point did you take from which to calculate the height?
The ground
The
to
ground.
where we expect it to fall.
This ground, yes? But could I not have also taken the ground floor of MSP?
Yeah.
Yes. Will that mean it will change the number, yes? Because the height is going to be a bigger number. Will it change the physics?
I mean, we're introducing constraints, and here, depending on which constraint we introduce, the number is going to be different, because if we use this ground, we pretend that it can't fall any further, and when we use the ground floor, we're like, oh, we can still kick it down the stairs.
Yeah, but it's not going to change the physics. The pen's not going to fall differently if you decide
Exactly,
zero to be
that's
at
my
the
point.
ground.
The number will change. Whether I'm going to choose the ground floor as my 0 point of the height energy, yes, potential energy due to height, or whether I take this particular floor, the number of the potential energy due to height will change, but the way that the pen will fall will not change, right? To phrase this in the exact same, or slightly different, but the exact same point, is that the 0 point of energy is not defined. You're free to choose any 0 point of the energy that you want. Just questioning, have you seen and or heard this before?
Yeah, but that's only for potential energy. No?
Yes, but I'm talking about potential energy at this point, yes. So the 0 point of potential energy is not changed, right? So the 0 point energy is different depending on how you choose your, well, how you choose your 0 point. But the physics will not change. The pen will not drop in any different way. Now, for people who want to look it up, the broader mathematical picture of this is called engage in physics. And for people going to electrodynamics, we're going to talk a lot about these things back then. But the point here is that you can have situations where the numbers might be slightly different, but the physics will stay the same. The potential energy due to height is one of those numbers. The reason that the physics does not change, let me go back to here for now, your classical physics, is that how fast the pen will fall if I drop it is not due to this number itself, 20 joules compared to whatever number I got if I would have measured it from the ground floor. It's the change of this number. It's the change of this number, how much this number changes, that determines how much velocity the pen will get, right? Now, if I have 20 joules from here to here, and I will drop it, it will lose 20 joules of height energy, agreed? That energy will go into here, that gives you a certain amount of extra velocity. If I would have done the same exercise, but I would have started from all the way down as my 0 point energy, let's make it 200 joules, it's ridiculous, I'm just making up a number, but suppose that I have chosen a 0 point where the height energy now is 200, on its way down to this particular floor, it will still have lost 20 joules. Agreed? It was started from a different number, but the loss of energy will still have been that same 20. So that means, yes, you had a different number to begin with, but the amount that you lose and therefore transfer over to velocity will have stayed the same. So this is why the physics of the falling pen will actually be the same, even though your 0 point was different. To say the exact same thing is slightly different, in physics, only the change in energy has a physical interpretation, not the amount itself. It's a change of energy. Now, give me a second to complete this thought. I'm sure, by the way, that if you look back at either your high school or your classical mechanics that you did here, you must have picked it up somewhere, but I'm making this point very clearly now, I hope. Where you choose a 0 point of energy will only change the amount that you started with, but not the amount of how it will change, and therefore the amount that your velocity, your pen will gain will not change. The 0 point has no relevance whatsoever in physics at all. It's a change of energy that has a physical interpretation. So 0 points of energy are not important. But hey, that means you're completely free to add 100 to it, right? Sure, it will change the total number. In fact, you might actually add 100 here. It will change this number. It will still not change the 20 joules that you lose.
Yeah, but you said earlier that the mass actually changes over time, so the 100.
Now my question was if it did.
Oh, okay.
And unless it's decaying.
Yeah, but let's
Like
say it's
your
not
rocket.
decaying or something.
Okay, if it's not decaying, fine.
Yeah. Okay.
So can I add 400 to it as well without changing physics?
Sure, whatever.
Yeah, sure. Can I minus 1400? Is that okay? Yeah. If I have a situation where indeed I'm going to leave out the nuclear part, so the mass does not change, or I'm not going to have a rocket that boosts matter out. So I'm specifically going to go to a case where the mass is constant. And we're free to add this without changing the physics? Yes? The only thing that I did, if I look at a situation where the mass is constant, is that I shifted the 0 point. Yes? But because the 0 point didn't have any physical interpretation to begin with, you might as well left it out. Just as easily as you can add 100 or minus 1400 to the total budget of energy, the change of energy will not change. You might as well add mc squared to it if you want. So this is the reason why in your classical physics you never had to worry about the mc squared. The only thing the mc squared was change the 0 point of the energy, did not change the physics. Okay? So, yes.
Okay, so that was fine because then you can also take the derivative and make the whole energy disappear and then
That is
solve
correct.
for that. So that's what we used to do. But in the case of a rocket that we managed to actually solve in classical mechanics, and
Yes.
apparently it's possible to land rockets on the moon just by using Newtonian physics, then you should take into account m squared, c squared.
Agreed. At the moment that you're going to look at situations where
squared.
this
MC squared.
this 0 point energy, if you will, right?
Mhm.
That the mass of the situation is indeed time dependent, you will have to take it into account.
But so you can't use only Newtonian physics to put a ship on the moon, because like in Newtonian physics you wouldn't have this part there, so you like be missing some kind of energy.
I think because c squared is so big, the change in mass would actually be like negligible.
That is correct.
I think also it depends on how you define your system, because even if with your rocket, if you define your system as the rocket and the fuel, then that mass will still not change. No?
Well, I mean, but his situation is suppose that you have some
With the
circumstance where
nuclear.
the mass does change,
Yes.
not due to relativity, but simply because you're jettisoning fuel or something like that.
Yes.
Then it means it is time dependent, and you cannot see it as a constant
Just-
contribution.
yeah,
Yes.
you can't just delete it.
No, I agree, but then you cannot just delete it. But then Timon's argument is actually correct. The change of the mass that you would end up with is so ridiculously small due to the bigness of c squared, you might as well ignore it. By the way, next week I'm going to drop the situation now where things are accelerating due to boosting and these sorts of things. Next week I'm going to derive those sorts of things, and you're going to see this in more detail. My only point right here, right now is that the reason that you never had to worry too much about the mc squared in your classical physics, again, in situations where m was constant, yes, because the 0 point didn't have any physical interpretation to begin with. You're free to add it and subtract it at will. Okay? Joe, you had also a question, I think, but
doesn't that assume mc squared is constant throughout it?
yeah, that's the same comment. We are assuming right now that the m is constant, therefore mc squared is
I
constant.
thought the question was why could you assume that?
Let's be sure. You understand this point up till now, yes? Okay. My original phrasing was, could you have added? Could you have, if you knew that mc squared was there, could you then have said that the loss of potential energy was not transferred just to potential energy, to kinetic energy, but also a little bit to change in mass? Yes. And then we said, well, if you are in a situation where the mass is indeed constant, then this is just a arbitrary shift in 0 point energy,
Yeah.
and you might as well drop it.
But to show that it's constant, you have to assume that it's constant.
Yes, but again, next week I'm going to show a situation where mass can indeed change. All of this is just to show you the 0 point energy was shifted, so that means in cases where the mass is constant, you never had to worry about this. And this is why probably you never did before. one last thing, and then I'll have to continue. Yes.
If we never cared about it in classical mechanics,
Yes.
then why do we care about it in relativity?
That is a very good question.
Because it's constant.
No, I agree. That's a very good question. So the question now is, okay, sticking to the situation where mass is constant, this is just a arbitrary shift in 0-point energy. That means you didn't have to worry about it in classical physics, so your books or your teachers never did before. Why are we going to care about it now? Yes? I mean, we saw that the thing comes out. Why do we care about it anyway then? Doesn't the same argument hold in special relativity now? I mean, you have, you have a shift in energy, but we've just been discussing all this time that the shift in energy doesn't have, or the 0 point doesn't have any meaning. So why don't we just drop it? Just like we did in classical physics. I'm curious if somebody can guess an answer. We're not going to drop it, okay?
Maybe it gives like a minimum energy from every reference frame?
Correct. We already discussed that. In, again, classical physics, where you could easily shift your 0 point by adding 1400 or plus 400 or whatever, that number was completely arbitrary. You know, I just, as we say in Dutch, I suck it out of my thumb. I'm sure in English there's a similar expression that we're not going to say on video, okay? Yeah, let it rest for a second. Okay. The reason is that because that number really came out of nowhere. Now this particular number, MC squared, doesn't come out of nowhere. It comes directly from the Minkowski line element. I have no business putting it away. And Sam, how did you phrase it just a second ago?
If we never cared about it in classical mechanics, then why do we care about it now?
Yes, but there was an answer as well.
The who, the what? Yes.
Yeah, you gave an answer a second ago, didn't you?
No, I didn't.
Who was that?
No, it was Jonas, I think, that gave
Oh,
the
Jonas,
answer.
yes. Sorry, guys. Yeah, you look like.
Very much.
Not at all.
Definitely.
Okay, so here's a question, there's the answer. Okay, the question is, if MC squared is just a shift in 0 point energy and it doesn't have any meaning anyway in classical physics, why do we keep it in special relativity? And then you get the answer.
Yeah, then you have like a minimum energy from any reference frame.
Yes, we saw that this energy really has a physical meaning. It's an energy you cannot get rid of. Yes? It's there anyway, always. So that's your argument. I gave a slightly different argument, and that is that when I came up with my minus 1400 or plus 400, I sucked it out of my thumb. That number came from nowhere, had no physical information in it whatsoever. This one does, because it's directly connected to the mass, so it really has physical interpretation. Now, there's also a mathematical reason, if you will. The mathematical reason is, if this is our starting point, and that thing gave us it, then apparently I have no choice but to keep it. If I'm going to throw away MC squared here, then that means I'm throwing away something here as well. Yes?
Is this total energy then invariant, or is it still not?
It's still not invariant.
Okay.
Yes, and that's because of this V, yes?
Yes.
So it's still not invariant. Yes?
For the special relativity, shouldn't we then drop mgh because
Yes.
it has no gravity?
That's correct. The mgh I put in there because I talked a little bit about classical physics. Now let's go back to the main narrative here. What we found, right? We found this expression, and we're discussing some subtle points there. So just to finish that particular discussion, what we see here is, first of all, there is this particular amount of energy, the lowest amount of energy that something can have, and you cannot get rid of it no matter to what inertial system you go. Secondly, that zero amount of energy, mc squared, is directly tied to the physics. It's not a number that I came up with as a 0 point. Physics came up with it. So I have no business throwing it out. Okay? That was the whole point here. Final point, the reason that you did not care about this thing in Newtonian physics is because the 0 point energy you might as well drop out. We're going to leave it in. Good. Final comment, and then let's go to a break. This P here, so forget about the energy now. As far as I'm concerned, this is now, for now, a fixed matter. Again, just like I'm not going to draw rel under this to indicate that I mean relativistic energy as opposed to 1/2 mv squared classical energy. anytime that I'm going to write capital E, I mean this version of the energy, yes? Okay. Now, in very much the same way, let's talk about momentum for a moment. This relativistic momentum we saw was defined as gamma times the classical momentum. Yeah? Or, if you want, it looks like this. Now, just as it did with the energy, that you look at the situation where vacuum cleaners are not flying too fast, let's do the same thing here. Let's look at the situation that the vacuum cleaner is flying not too fast, and now we're measuring not its energy, but its momentum. This is wrong. I think this is correct, huh? Yes? Am I missing something?
No, just a comment. Can you from this say that you cannot go, if you have mass, that you cannot go with the speed of light? Because
Oh, that's interesting. Why?
because if mass is something, then you have something over infinity, so that would mean that P would be infinite, that means that the energy would be infinite. But if mass is then 0, we have 0 times divided by infinity, and maybe
Sounds like such a nice way to end the first half before we go to break. Let me get back to that in a second. Yeah? You are right. The answer is yes. I'm going to share it to everybody in a second. Now, this is our relativistic momentum. We got it from the Minkowski line element. And if we're going to look at a vacuum cleaner, it's not flying too fast. V is small compared to C, then that means this approximation that we had here applies again. It will look like this. And then you will get, oh look. The relativistic momentum is your basic classical momentum, m times v, plus an extra part. There is a unit missing somewhere, but oh, here it is. There you go.
Up top it should also be the third, right? V.
Yes, you're right. Thank you. There you go. So, just as we could see that the relativistic energy reduces to the classical energy if you look at things that do not move too fast, the same thing holds here. The momentum, if the thing happens to move very slowly, will reduce to the classical one that you knew from Newtonian physics, yeah, plus a little extra. The little extra is probably very small because you're divided by c squares, right? So it is probably going to be a small number. So that means you don't have to worry about that term usually when you do, again, your classical physics. So that's kind of neat. Now, I would expect this, to be honest. If I'm going to derive new rules for energy and momentum, using a theory that is bigger than Newtonian theory, I expect my expressions to look the same plus extra, yes? Well, that's exactly what you see happening here. I mean, if I would not have done this calculation and you would ask me, and I would have been smart enough, I would probably said, well, if you're going to make your Newtonian situation bigger, going to special relativity, I expect at the very least to get back your original results, plus extra stuff to compensate for the fact that things might now go very fast. That's exactly what you see. You see the exact old expressions plus extra stuff due to you moving very fast. The same thing with the energies. Yeah. So I think everything is completely in line with maybe what you would expect. And everything, again, just came from this and some algebra. Now, let's go to Alitza's point. Nice way to end the first half. There's one final comment you can make based on this energy here. I think in at least one of the tutorials, as in sort of a tangible, tangent discussion, I already mentioned this. This is the energy that, according to relativity, a flying vacuum cleaner has, right? If I see it fly by, it will have that energy. I have to put in the V that I measure for the vacuum cleaner. This is the energy that apparently the thing has. You can rephrase that statement as saying, if I want the vacuum cleaner to have accelerated to that velocity, then this is the energy I should have put in. Right? What happens if I want to accelerate the vacuum cleaner to the speed of light itself, v. How much energy should I put into the vacuum cleaner? Now you're one person say infinite and another person nodding along. Can you see from the formula itself? If I try to make the vacuum cleaner, and in my frame that thing goes with the velocity v, if I try to make it go with the speed of light, then this is the energy that I need according to relativity. Now if I put v as c in, because I want the vacuum cleaner to go with the speed of light, I will get mc squared over 1 minus 1, infinity. So that means it's going to be required an infinite amount of energy for me to get the vacuum cleaner to go with the speed of light. That's physics for saying this cannot be done. An infinite amount, yes? Question? Yes. This conclusion holds in that particular frame where the thing will go with the speed of light. But maybe if I go in another frame where it does not go with the speed of light, maybe I can sort of circumvent this conclusion.
But we proved that if anything goes with the speed of light in one frame, it does so in every other frame.
Correct. We had already proven from here, a couple of weeks ago, that if something goes with the speed of light in one frame, it will go with the speed of light in all frames. So that means this conclusion, that it takes infinite amount of energy, holds in all frames. That means not only is there not one frame in which you can accelerate something with the speed of light, there is no frame in which you can do it. Here finally, after many times pushing the statement, is one of the reasons, or one of the proofs, that things with mass cannot go with the speed of light.
But in the beginning, like one of the lectures, you said that c, we were doing some proof. You said that c isn't defined as the speed of light in this in that first statement.
Agreed.
The variance. So it's just like saying it can go faster than the number in that, but it's not saying it's the speed of light. Right?
I agree. That's a very good point. Thank you for pointing it out. When we re-derived special relativity in week 2 using the Minkowski line element, rather than the speed of light being invariant from week 1, I made a very explicit point that this c is a number that you should put in to make sure that the units come out all right. You had no mathematical choice but to put a velocity in there. And I made the point by saying, well, there is a c in there. I'm not saying that it's 300,000 kilometers per second. I'm not saying that light goes with that velocity. Right?
Yeah, it's just again that you can't go faster than that number in that statement.
Then let me rephrase this statement. It says if you want to let vacuum cleaners go with the velocity that I had to put in the Minkowski line element in order to make the units come out right, that will cost an infinite amount of energy. That is the right way to put it. It really is. So how do we know that it is actually the speed of light?
Experimentation.
That's experimentation. The best I could do at this point was tell you that there should be some velocity in there and that this velocity comes with special properties, and then experiment has to tell you that actually it is the speed of light. Not light itself, there's other things that go with this velocity. That number happens to be 300,000 kilometers per second. But that's a good point, thank you.
Would it be possible that
Yes.
there would be different values for c, that there would be different velocities in nature?
No, that would be so
Same.
cool, right? I mean, actually this is a question that a good theoretical physicist will come up with. Namely, maybe nature doesn't come with one of these numbers that must go into the Minkowski line element. Maybe nature has 5 of these numbers. And we've happened to have only just found one of them. That's a good question. So that sounds like a nice bachelor thesis research. Suppose that you have 5 of these different C's. How would nature look?
Doesn't that immediately contradict itself? Because what we're saying is that if you see one thing going slower than c, you see everything going slower than c.
No,
So
it
that
just
would
means
hold for all the 5 c's.
No, that
Meaning that
So suppose that you have 3 different C's, yes?
yeah.
We're sort of doing a bachelor research right now, okay? But let me just, because the argumentation that we did for RC, that one C that we think that there is only one of them, we saw that there is a barrier here. If something is on the left side of this, it will be on the left side in all frames.
Okay, I see.
But now you have 3 barriers, so you have different compartments of physics, if you will. Anyway, that sounds like a beautiful bachelor thesis research.
So for sure.
Or project. Project. That would be a good project. Period 6.
So we found also is like for sure the minimum, right? The minimum C, the smallest
No,
C.
that, again, I love this. I mean,
RC is
this
the
sounds like
smallest
such a
one.
cool project to do in period 6. Okay, so suppose that you have many of them, and experiment has only identified for us this one.
Then it's for sure the smallest one because we've
Because we haven't, but maybe there beyond that C, there's other ones, and there's different compartments of physics. Anyway, not for now.
Different
more
compartments.
like a
of
PhD
physics.
research.
No, not PhD. This is probably bachelor. Yeah, maybe master. But
No.
anyway,
PhDs.
Or a 6-week, 4-week project apparently.
it depends how
I
deep
mean-
we want to go. Yeah, but
Let's find a new C.
okay, guys, let's have a break. Okay.
I don't like the number.
I gave you a summary here on the board. Once you have this particular statement that apparently the rules of space and time obey this sort of strange minus sign version of Pythagorean's theorem, this from week 2 onwards is where we derive every single thing from, including everything that's on the board now, yes? This we had seen before, this guy, this guy, this guy, and all the rest is what we derive today. All of this from the Minkowski line element. That's a promise that I made in week 2. Every single special relativistic result comes only from that one statement. So, this is what we now concluded before the break. Yeah? I'm going to make one more comment before giving you an introduction to Lagrangian physics. Note that I explicitly wrote that a mass can take. Because if you go back to this expression here, by the way, between the brackets here means classical version. We're going to use these exclusively, yes? I'm just writing this for completeness. Now, this expression we saw it before the break means that if vacuum cleaners have to go with the speed of light in your frame, you have to give it infinite amount of energy, which is another way of saying you cannot do it. We also saw there's no frame in which it can be done because the speed of light has the same value in all. Yes, that's this statement. So really getting all our different results, stacking them together, getting all of this. But in this expression, E equals mc squared over 1 minus v over c. This conclusion we drew from this guy becoming infinite at the moment that v equals c, yes? Because then the denominator of this particular fraction becomes 0, and you get number over 0, which gives you your infinity. Now, in principle, there's nothing stopping you from saying, but what if the thing that you're looking at, the vacuum cleaner itself, has no mass? You get 0 over 0. Now, mathematicians don't like zeros over zeros, because it's indeterminate within mathematics. It doesn't mean that the answer does not exist, it simply means that the formula cannot give you that answer. But that leaves at least open the possibility that things can go with the speed of light under the necessary but not sufficient condition that that thing then should not have mass itself. I say necessary because that's the only way you can counteract the 0 in the denominator is to make it a mass 0. That makes it necessary. Doesn't make it sufficient because you get 0 over 0, which is indeterminate. And indeterminate means it might still be infinity, it might still be impossible. So it's necessary to have 0 mass if you want to go with the speed of light. But you still have to find out whether it can still work. And I do recall saying this in one of the tutorials. The fact that this is indeterminate for mass is 0 with the speed of light doesn't mean that the number does not exist. It simply means it cannot come from this formula. So you need a formula outside of special relativity to tell you that number, because special relativity cannot do it for you. That number we know from quantum mechanics. We know that in case of light, what the energy is. The energy of light, of a photon, is h bar times omega. Yes. So apparently, this number does exist for massless particles. It's just that the number itself should come from outside of special relativity. So conclusion here that we see is that the c is the highest velocity mass can have. But we have a stronger conclusion now. It means things that have no mass must go with the speed of light. That's a very strong conclusion. Not only is it so that things that go with the speed of, that have mass cannot go with the speed of light, the opposite is also true. If something does go with the speed of light, it must be massless. That's a strong conclusion. Here's the delivery service. Oh, I'm sorry, no. Sorry, so no, I knew that there were people coming in with waffles and we knocked it out. What was that? But
Unfortunately, no.
You'll get a vote out, please.
Okay, now that we already stopped, there is like the second conclusion. You said that C is the highest velocity mass can have.
yes.
No, mass cannot go with C.
Oh. Highest
C is highest velocity mass can't have.
This is the highest velocity, and you can't have it.
Limiting velocity, is that better? Okay, good. Okay, so we have strong conclusions now. We have really learned something just from the rules of space and time itself now about energy and momentum. Now, that was the learning goal number 1, to give you the rules of energy and momentum in special relativity. Now, I promised you to also talk about Lagrangian mechanics. Most of that we will derive during the tutorial, so what I'm going to give you now is a plug-and-play version, but the details we're going to do in the tutorial, yes? Now, to already give you the narrative, I'm going to show you how Lagrangian mechanics is done, why it is done that way, and then in the tutorial we're going to use the Lagrangian mechanics to yet again get these conclusions. Yeah? But now in a much more formal way. Small introduction, the reason that we do Lagrangian mechanics is not because it's particularly necessary in special relativity. Look, we already have the answers. But the reason is if you want to become or do anything within theoretical physics or particle physics, subatomic physics, these sorts of things, or quantum mechanics, then all of this is done by Lagrangian mechanics. So you have to have picked it up at some point, yes? So if it's not for this particular course, but you follow courses, this is why the physics team decided, let's do this in Lagrangian mechanics. So, just out of interest, who has seen Lagrangian mechanics in any shape or form, even if you don't know the details before? 3, 4, 5 people? Okay. So,
Ronald skipped that
I know.
chapter.
It's in the classical mechanics course, there's 1 week for this. Whereas a real full understanding requires, a 1 month course or something like that. This is why I'm going to give you a plug and play version. Okay guys, here's the plug and play version of Lagrangian mechanics. Smart people, including Lagrange, noticed that the laws of physics can be mathematically recast in a different form. And the different form it looks very abstract, but it has the exact same physical content as, say, Newton's laws or any other piece of physics. The form that we're talking about is the so-called Lagrangian formalism. And here's the plug-and-play version. Okay? A piece of physics can be represented by a particular function that we call capital L, the Lagrangian. Now, what is a Lagrangian? Well, it's a function. And the function depends on, well, the type of physics that you're looking at. But suppose that we're looking at our flying pen again, yes? Classical physics. Then a flying pen has 2 numbers that you want to know if you want to know how it flies. You have to know where it is at any moment in time. And at any moment in time, you have to know where it wants to go. Yes, its velocity at any moment in time. Once you have those 2 functions, then you can completely in time describe where the thing will end up. Now, you can construct out of those 2 numbers how your flying pen will look. You can construct a new function that we call the Lagrangian. How this Lagrangian looks is highly dependent on the context. So I'm going to leave that open for now. This is what makes it abstract. I'm going to leave it open, yes? Now, here's the following step. You're going to take your Lagrangian, you're going to integrate it over time. Now, why would somebody do that? You have this unknown abstract function of your flying pen, and that thing you're going to integrate over time. Okay. Highly abstract, right? The outcome of this thing is going to be a number. you see why it's a number and not a function? The whole Lagrangian, via the t that's within the flying pen's velocity position, that makes the whole Lagrangian ultimately a function of time, right? But if you integrate a function of time over time, from 0.1 second to 10 seconds, you will get back a number, agreed? So some number will come out. Now what number comes out? Maybe the number is 100. Maybe the number is -3. Maybe the number is infinite. It could also be minus pi to the power e. Yes, some number. What determines what number comes out, whether it's any of these options or this whole series of other numbers that could have come out, is dependent on, well, x and v, right? If you would have put in a different flying pen with a different velocity, well, that means the function you're integrating over is going to be a different function, so the outcome is going to be a different number. Yeah? The question that people now ask in Lagrangian physics is the following. If I have a flying pen, how will it fly? What is my x as a function of t and what is my v as a function of t? What are these two functions? And Lagrangian physics states the following. And for the people who want to continue in physics, this has to be, you know, this big in your notebook. There's a rule in physics. Maybe it's I'm not exaggerating here. This might be the most important rule in physics that we have. It's not the conservation of energy. It's not the rise in entropy of these sorts of things. This, to the best of my knowledge, is the biggest rule in physics that we have. This guy, this capital S, the integral of the Lagrangian. The guy is called the action. Here's the rule of physics. Does classical mechanics and flying pens and relativity know all of physics? All of physics will obey this rule. What will nature do? I'm not done yet with the writing, yes, grammatically correct, there's still a part coming. What will nature do? If you want to know how your pen flies, or any other piece of physics, your nuclear physics, your optics, nature will choose this function and this function, the function that you don't know yet, your flying pen, such now that's super abstract, isn't it? You have this function called the Lagrangian, you integrate that thing, and of all the possible outcomes that you could have gotten, right, for every x and every v functions there's a different outcome. Which of the x and v does nature actually make your pen fly, or your physics go, or your nuclear physics go? It will always choose the one. The x and v is such that of these possibilities the smallest will come out. In my example, there will be this one. Yeah? Yes?
Just to double confirm, the Lagrangian is, like, dt is the change in energy, right? So what you're doing is you're integrating over the change of energy and minimize that energy.
Why is it a change in energy?
No, I'm just, that's as far as, so how I understood the Lagrangian so far. I just wanted to double confirm that my understanding is right.
That is wrong.
Okay.
Okay.
Good.
Yes. No, we'll get to the right interpretation, yes.
How would we know that this integral is the smallest of the s?
That is a good question, because I have no choice for you but to accept this as a rule of physics. Where does it come from? From the exact same place where F equals ma comes from. People did measurements and measurements and more measurements, and then they found, wait a minute, there's this underlying mathematical structure. Why is it this structure? Because it is. It's just like saying the rules of space and time. Why is it a separate time and a Euclidean space as you did in Euclidean physics? Well, it turned out, apparently, that nature chose this particular option, yes, instead. In very much the same way, nature has decided that this is how nature operates. I cannot stress enough, this should be where people want to go, especially into theoretical particle physics, this must be maybe one of the biggest takeaways from this lecture series. Yes, every single piece of physics can be written in this particular formalism. Now, your question, entirely correct, is okay, we have a rule now. You have to choose your x and v such that of all the infinite options that could have come out, you have to pick the one that make the action the smallest. It's called the principle of minimal action. That's what this rule is called. Spiel's question, if I rephrase it correctly, was, okay, but how do you know of all the possible x as functions of t and v as functions of t, how do you know which one makes this integral the smallest? Right? If you know that you have to look for the x and v that makes this integral small, which of the infinite many xt's and vt's should you have taken? Now there's two ways to solve this issue. One of them is you try every single x as a function of t and every single v a function as t, and you try every single integral and just go through the infinite list and look for the smallest number. It's not impossible, except it takes you an infinite amount of time because there's infinitely many possibilities. Yes? Fortunately, that issue is solved. It's a mathematical exercise, if you will. Let's make things a little bit more definitive. Suppose that I would have had this. Yes? Suppose that this was my integral, my action. If this had been a parabola, then it would have looked like this maybe. T squared, right? Some number would come out. But maybe it was not a parabola, maybe it was a logarithm of t. One over t would come out, and then some numbers, right? There's infinitely many possibilities, so which one do you choose? I'm going to give you the solution in a tutorial. We're actually going to derive why this is true. But I told you I'm going to give you a plug-and-play version. So here's the answer to your question. How to know which delivery service? Indeed, yes. You have what? Wow.
You're much appreciated.
Excuse me.
Thank you.
You're making the back row so jealous now.
Oh, we're still selling, so you can come to us in the break.
We had a little agreement that I would say this and he would make some... Here's the answer, the mathematical answer. We're going to prove this particular rule in the tutorial. It's as follows. How do you know which x and v to choose to make the integral the smallest, the action? Take your Lagrangian, this guy. Put it into this equation, you get a left side. Put it on this side of the equation, you get a right side. Then this equation is going to be a function of x and v's, agreed? If you know what L is as a function of x and v, and if you put it in here, you will get a relationship between x and v. That particular relation is the one that nature will choose. That is the one that will make this integral come out the smallest. So, the answer to the question, when is the action minimal, for what x and v is that the case? It's the x and v that solves this equation. So really, the question, how does nature behave, is given a Lagrangian, given a particular description of nature. If I give you a Lagrangian, I ask you, here's a Lagrangian, tell me how nature behaves. You take my Lagrangian, squeeze into this equation, you will get the answer. This is so important that it has a very well-known name in physics. It's called the Euler-Lagrange equation. So far so good? Super abstract, right? Now, again, in the tutorial we're going to practice with a couple of these things. But my promise to you was that I would tell you why people use this instead of Newtonian physics, say. Newtonian physics is so easy. Somebody gives you a force, the expression for how many newtons a particle feels, or a pen, or a fish, or nuclear physics. You squeeze it into Newton's second law, F equals dp dt or so, and then you end up with how nature behaves, right? This is how you do classical physics. Somebody gives you a force, you put it into Newton's law, do the math, you get how nature will behave. But this is very much the same. Instead of giving you a force, I give you a Lagrangian. And instead of you plugging your force into Newton's second law, you plug your Lagrangian into the Lagrange equation, you do the math, and you end up with the result. So it really is the same style of reasoning, right? You're given a particular description of nature, a force in Newtonian physics or Lagrangian in Lagrangian physics. You take the thing that you were given, put it into a rule in Newton's laws, that is in Newton's physics that will be Newton's second law. Lagrangian physics that will be the Euler-Lagrange equation. You do the math, and then both of them will give you the answer. The answers are going to be the same always. So in that sense, it's not different from what we did before. It's just that, well, your intuition is more familiar with forces, right? This is my example with my cat. My cat understands pushing and pulling, how that works. My cat does not understand Lagrangians. Or she hasn't told me at least. Okay? But mathematically speaking, we're not doing anything different. Now, if you think, well, but I like Newtonian physics more because at the very least I sort of understand what a force is, then I have to ask you to ask yourself, do you know what a force is, or is it just because you were raised knowing what forces are? That somebody in high school, maybe, again, constantly, I'm reaching our high school teachers, I'm not, but could it be that maybe the only reason that you're familiar with forces is because maybe you had a little booklet that told you the forces for different situations, right? In Dutch we have this binas, this little booklet that tells you the forces for every single situation. Have you ever wondered where those forces came from? Well, it's in the booklet. Maybe somebody measured it. Those forces come from just as deep a dark a mystery as our Lagrangians are going to come from. Somebody guessed a force, put it into Newton's laws, came up with a description of nature, then tested whether that description was correct. If so, then your guess for the force was correct. And when they tested it over and over and over again, they put it into a little booklet and gave it to students. Yes? In very much the same way, in Lagrangian physics, somebody guesses a Lagrangian, puts it into this rule, comes up with predictions, test, and at some point you find this is apparently the right Lagrangian. So I'm emphasizing here that it's really the same abstract series of steps that we're doing, and the reason that you find Newtonian physics probably more familiar is only because you're so much used to them and you're sort of used to knowing the forces because somebody taught you that from when you were young. Yes. So that's my point here. It's the same physics, it's different mathematics. Can somebody guess what the reason is for Lagrangian physics? It's a difficult question, but maybe you can sort of guess why people prefer Lagrangian physics over Newtonian. I mean, it comes with a price, it's more abstract, but why do we do it anyway?
It's much easier to describe because you can have a Lagrangian for a complex system, whereas with Newtonian, say you have a couple of degrees of freedom, oh, that's going to be often of work.
I think that's a very good first reason why Lagrangian physics is so ubiquitous in theoretical physics. One of them, it's Felix's point, is that Newtonian physics mathematically becomes very quickly very cumbersome. Now, when you do your Newtonian physics, typically you have a particle that feels maybe one force, maybe two, not too many. If you have more than one force going on, or more than five, things become very complicated. Solving Newton's second law is going to be an extremely mathematically challenging exercise. That's one reason. I'm going to add a second of my own. This guy is a scalar. Forces are vectors. Forces pull in different directions. Lagrangians doesn't have a direction. That's good. Because in Newtonian physics, if you want to know how your pen flies, you have to calculate it for at least 3 different directions, yes? Now, usually that's not too much of a problem because sometimes the force is exactly in the same direction as the thing was already moving anyway. So it becomes a one-dimensional problem by accident. But generally speaking, a pen flying through the wind and through gravity, many different directions going on at the same time, you have to solve 3 equations at once. Much more complicated. Sometimes, even though the law for the force itself is inherently 3-dimensional. I mean, the Lorentz force for magnetism is one example, right? The thing flies in this direction, the particle, in a magnetic field, yet the force is perpendicular to it. So that means the direction and the actual force are perpendicular. So that means inherently you have more than one dimension to worry about if you do it by Newton's laws. None of these issues you have with Lagrangian mechanics. It has no directions, so therefore it solves all the directions automatically for you. You don't have to worry about it. Yes?
I'm just saying we're almost 10 minutes over time.
Oh, I'm so sorry.
No, it's
No, it's good. Do you mind if I take 5 minutes more to finish this one? Yeah. We're going to get it back from the tutorial, you don't worry about it. But I do really want to have made this point, but thank you. Here's the final reason. Well, let me give 2 more. No, there's a whole list of these things, but let me give you 2 more. Short version. Let's go back to Newtonian physics. Yes? This law, again, it's a vector, but more importantly, it's given in x, y, z coordinates, right? F has a direction in, F has a certain amount in x direction, a certain amount in y direction, a certain amount in z direction. Suppose that for some reason I decide to do Newtonian physics, but not in x, y, z coordinates, but in spherical coordinates. Right? You know that you can write x, y, z coordinates into theta, phi, and r. Same physics, different mathematics. This law becomes ridiculously complicated if you go to a different coordinate system. Not an inertial different coordinate system. I mean, going from x, y, z to polar coordinates, cylindrical coordinates, what have you. This whole law messes up in itself, even before you put in forces and you try to calculate it. Lagrangians, exactly the same, doesn't change.
But if you put that in Lagrangians and you find v and t and x,
yes.
How do you find which direction it's going in that if you're saying that it's not?
You don't, it's a scalar.
I will show you
Okay.
in the tutorial. You will see an example. Yes.
Isn't like you put like 2 vectors into the function, but it outputs a scalar?
Yes.
Okay.
That's possible.
Yeah.
But there's an underlying question that I sort of feel bubbling underneath your 2 questions. Namely, if nature has 3-dimensional motion and things going on, how can it be described by a 1-dimensional thing? Yes, that is really the deeper question here, I think. The question that it can is really the answer why Lagrange, or one of the answers why Lagrangian physics is so popular under theoretical physics. You don't have to worry about it. It will automatically do this for you. Here's my final reason. I'm going to write down an expression now. Suppose that you take a Lagrangian. You take its derivative with respect to v. You multiply that outcome with v. You subtract again the Lagrangian. You get a new number. Actually, this is not a number because it might still be time dependent. This guy that comes out is the energy of the system. So why are Lagrangians handy? It means that if somebody has given you a Lagrangian, via this trick you find immediately how nature will behave. Via this trick you have immediately the expression for energy. For any system in nature, throughout all of nature. Now you know the expression for energy in classical mechanics, right? 1/2 mv squared plus potential energy. But if I ask you, tell me what the energy is of an electromagnetic field. Do you know by heart? I happen to know it by heart. Well, it is this, yes. But if you didn't know about that, and I would ask you, here's an electromagnetic field, tell me the energy, After painful mathematical consideration, you will find it's the electric field squared plus the magnetic field squared integrated over space. Okay? Now, I happen to know this by heart. Lagrangian mechanics gives you immediately the answer. You know what else? In this exercise we're going to do in the tutorial, Lagrangian mechanics tells you that this is constant. For any system. It's the proof of the conservation of energy. It comes from Lagrangian mechanics. Once you know that this is true, and somebody is giving you Lagrangian, not only can you calculate what the energy of that system is, you immediately know that it's constant. Conservation energy is not an experimental fact, it's a mathematical fact. It comes from Lagrangian physics. So, what are we going to do in the tutorial? A couple of exercises having to do with this, but we are going to apply this rule. I'm going to let you apply it to Lagrangian version of special relativity. Calculate the energy using this. And not only do you get back this, you already knew this from my quick and dirty way, you will also know that it's constant. And that we didn't know before. So here's the tutorial.